Welcome to the deep dive. We're here to stack up the info, cut through that noise, and give you the insights you really need. Today, we're plunging into something, well, truly foundational for, our whole digital world. But it mostly operates behind the scenes. We're talking about atomic layer etching systems. ALE for short, think about your phone, right? That tiny supercomputer, or the huge data centers powering the cloud. None of that works without the incredible precision of ALE. So our mission today, a real deep dive. We want to show you why this tech isn't just important, it's absolutely indispensable, really, for the future of
It's
electronics.
spot on. It's definitely a hidden hero. At its core, atomic layer etching.
Hmm.
It's a really revolutionary technique in semiconductor manufacturing, a precision technique. See, unlike traditional etching, which might just kind of blast away material, ALE is more like atomic scale surgery. It works with this precise two-step chemical process. So first, a gas adsorbs just one atomic layer onto the material
Yeah,
surface.
just one layer, wow.
Exactly, just one. And then a different reactant comes in and it removes only that specific layer. This gives you just unparalleled control. We can remove material, literally one atomic layer at a time.
Oh.
And that level of precise patterning, that's what enables these incredibly dense, complex, advanced semiconductor nodes. They're the building blocks, really, for every high-performance logic chip, every memory device we rely on today.
Atomic surgery versus sandblasting. I like that analogy. That really paints a picture. And for this deep dive, we're pulling our insights from a recent market analysis report. Cognitive Market Research put it out. So we're not just looking at the tech itself, but also, the business side. The dynamics of this niche, but like you said, incredibly vital industry.
Okay, so let's zoom in on that foundational role, ALE in modern tech. That controlled layer-by-layer removal for precise patterning. It sounds incredibly complex. Why is that level of precision so, well, utterly indispensable, especially for these advanced semiconductor nodes, the ones really pushing the limits? Yeah, it's really all about pushing past the traditional scaling limits. You just can't get there otherwise. This atomic precision is basically non-negotiable now for creating smaller, more energy-efficient devices. Think about it. Every generation of chips, they need to pack more transistors into the same space, or even a smaller space.
Right. Moore's law in action, sort of.
Exactly. And without ALE, well, we couldn't create the incredibly fine structures you need to prevent problems. Things like signal leakage in advanced logic chips, or, to increase the bit density in memory chips.
Ah,
It's fundamentally how we keep making devices like your smartphone thinner, more powerful, and, crucially, last longer on a single charge. It really dictates how many transistors you can cram into a tiny space and still have them work reliably.
that really sounds like the ultimate enabler then, for miniaturization, for efficiency. And when we talk critical technology, well, the market shows it. It's demonstrating some explosive growth. The report we mentioned from Cognitive Market Research, they estimated the atomic layer etching system market, what was it? Around USD 1.35 billion in 2023.
Yeah, 351.2 million to be precise. And that's a significant figure, but honestly, it's just the starting point. The market's projected to reach, get this, over 2.5 billion USD by 2032. That's 2,500.9769 million,
Wow.
which shows a pretty substantial compound annual growth rate, the CAGR, of 8.00% over that period.
8% CAGR, that's strong.
It really is. And this isn't just a number, right? It signals something fundamental. It means the underlying fabrication capability for all next-gen electronics is expanding significantly. It points to a long-term investment cycle that's, it's far from over.
Over doubling in less than a decade.
Yeah.
Yeah, that really underscores how critical this tech is becoming. Okay, let's unpack this a bit. What's fueling this kind of expansion? What are the key drivers behind such substantial demand for something so precise, so specialized?
Well, it's really a confluence of factors hitting all at once. First, like we touched on, is that just insatiable demand for smaller, more energy-efficient devices across the board. Everything. Phones, wearables, everything. Exactly. Then you layer on the rapid advances in these huge technologies like AI. Artificial intelligence needs incredibly fast processors for those complex neural nets. Then there's 5G, demanding efficient high-frequency chips for connectivity. And the Internet of Things, IoT, which needs tiny low-power sensors and chips for everything from smart homes to, industrial applications.
So many different areas needing better chips.
Precisely. And all of these require increasingly sophisticated semiconductors. Plus, the semiconductor designs themselves, they're getting way more complex. That complexity absolutely necessitates this level of etching precision. You just can't do it otherwise. And then maybe more broadly, there's just an overall increase in global semiconductor manufacturing capacity being built out.
Right, all the new fabs we hear about.
Yeah, and that directly supports the demand for ALE systems. So you see broad demand across consumer electronics, automotive, aerospace, defense, telecommunications. Plus, don't forget the exponential rise of data centers and cloud computing. They are perpetually hungry for more advanced semiconductors. That strengthens the need for ALE, too.
It's clear that innovation is a key part of this story, too. The source highlights a specific breakthrough. Alex Labs AB. They got their first European patent for something called Atomic Layer Etch Pitch Splitting, APS. That sounds like a potential game changer for pushing the boundaries even further.
It does. Pitch splitting techniques are crucial for getting features even closer together than standard lithography allows. Doing it with ALE precision, that could be very significant.
So with a technology this vital, this global, where are these systems actually making the biggest impact geographically? This is where it gets really interesting, I think. Who's leading the charge? Where's the most rapid adoption happening?
Okay, so looking at 2023, North America actually held the largest market share, about 35%.
Oh, interesting. Why North America?
Well, it's largely driven by consistent demand for really advanced semiconductor devices, plus robust R&D and nanotechnology. And, of course, the presence of numerous prominent semiconductor manufacturers, especially in the U.S.
Okay.
Europe followed, with around 30% market share. That's influenced by growing consumer electronics demand there and also the ongoing 5G network expansion. But here's the big shift, the Asia-Pacific region. In 2023, it accounted for about 25%, mainly China and Japan.
Right.
But it's projected for significantly accelerated growth. It's expected to increase its share to 28% by 2024 alone, and it boasts the highest CAGR among all regions, 10%.
10% CRGR for Asia Pacific. Wow.
Yeah. This rapid growth, it's not just about numbers. It really points to a strategic push in the region for self-sufficiency in semiconductor manufacturing. That's a trend with huge global implications, and it's expected to keep dominating because of ongoing innovation and expansion there.
So a really dynamic global race then. Asia Pacific is gaining ground fast, potentially reshaping the whole strategic landscape. And what about the companies, the competitive landscape? The report says it's intensely competitive, several big players. Who are the main names and how are they, navigating this high-stakes environment?
Absolutely, it's competitive. The major players are pretty well established. In 2023, Hitachi High-Tech Group held the top spot, market share around 21%. Lam Research Corporation was close behind at 19%. And Oxford Instruments Twank had about 13%.
Okay, so those are the big three for now.
Yeah. But they're definitely not sitting still. They're constantly investing and investing heavily in R&D, improving their systems, trying to keep that competitive edge. We're also seeing a lot of M&A activity, mergers, acquisitions, and strategic partnerships too. It's all aimed at expanding their product portfolios and their global reach.
Makes sense.
And looking ahead, say, to 2024 and beyond, the expectation is definitely for new entrants and even more competition, especially in those fast-growing Asia-Pacific markets.
Okay, so growth is impressive, competition is fierce. But it can't all be smooth sailing, right? What does this mean for the industry? Are there hurdles? The report mentions complexity and cost of implementation as significant difficulties. How tough is that, really?
Oh, it's a major challenge, and it's multifaceted. First, there's the sheer capital expenditure, procuring and deploying these highly advanced ALE systems. It's expensive, really expensive. It can be genuinely prohibitive, especially for smaller companies or maybe new entrants trying to upgrade from older etching tech.
So it creates a high barrier to entry.
Absolutely. It's not just a hurdle. You could call it a strategic choke point, almost. It means innovation often gets concentrated in the hands of just a few dominant players. Now, that can accelerate development because they have scale.
Right.
But it also creates potential vulnerabilities in the global supply chain if you don't have enough diverse providers.
Yeah.
And it's not just the cost of the machine itself. The inherent complexity of ALE methods that adds another layer. Well, implementing ALE demands very specific, highly skilled knowledge. You need precise control over all sorts of factors, gas flow, temperature, pressure, getting consistent results at this atomic level. It requires extensive training, a really skilled workforce. And that naturally adds significantly to the operational costs.
You need the expensive machine and the highly trained people to run it.
Exactly. There are efforts to address this, like Applied Materials, India, has this Ascent program. It's aimed at driving innovation and education in semiconductor equipment, trying to build up that skilled workforce.
Okay, so complexity and cost are big ones, but it's not just internal factors, right? Our source also flags market volatility as another key challenge. How does that volatility impact an industry that needs these huge, long-term, high-cost investments?
Yeah, that's the other shoe dropping, isn't it? The semiconductor industry is just notoriously cyclical. Always has been. It's heavily influenced by shifts in consumer preferences, what gadgets are hot this year, also broader economic conditions, recessions, booms, and just rapid technical advancements constantly changing the game. This inherent volatility means you get these unpredictable changes in demand for advanced tech, like ALE systems. So during periods of high demand, companies might invest heavily, pour money into ALE to boost production.
Gotta meet demand.
But then during an economic downturn, they might slam the brakes, delay, or reduce spending to conserve capital. And that lack of clarity, that uncertainty, it can really hamper long-term investment planning for the chip manufacturers. It creates this kind of precarious balance. You need the cutting-edge tools like ALE, but there's always the risk of overinvesting in what turns out to be an unpredictable market.
Okay, so significant hurdles: cost, complexity, volatility. But despite all that, the future for ALE still looks incredibly promising. What's fascinating here is what's next? What's coming down the pipe for this incredible technology? What breakthroughs, what applications can we expect?
Yeah, despite the challenges, the trajectory is definitely upwards. We're looking at several really exciting developments. First, just the continued shrinking of semiconductor technology down to nanoscale dimensions. As that happens, ALE's atomic level precision becomes even more critical. It's essential for creating these incredibly complex nanostructures. A major leap forward that's starting to happen is integrating AI and machine learning into the etching processes themselves.
AI in the fab. How did that work?
Well, these AI systems can learn from real-time data coming off the etching tool. They can then adjust process settings dynamically on the fly. The idea is to boost efficiency, increase production throughput, and significantly decrease waste while improving the yield, the number of good chips you get per wafer.
Smarter etching, basically.
Exactly. Smarter, more adaptive etching. We'll also see just generally improved monitoring systems for even tighter control and more consistent results wafer after wafer. There's a good example out there already. Lam Research has this Pulsus PLB system. It produces these specific films, aluminum scandium nitride, ALCN films. They're used for next-gen MEMS-based microphones.
MEMS.
Microelectromechanical systems.
Right.
Tiny moving parts on a chip.
Okay.
So better microphones and also radio frequency filters. These enhance everything from, consumer gadgets to automotive sensors.
And it sounds like ALE isn't just for traditional chips anymore. It's finding new homes in some really cutting-edge fields.
Precisely. That's another big growth area, the growing need for ALE in emerging applications. Things like quantum computing, which requires manipulating matter at incredibly fine scales. MEMS, like we just mentioned, the tiny accelerometers in your phone that detect motion, or the tiny microphone.
Right, the tiny machines.
Yeah, and also photonics, which is all about using light for things like faster data transmission. All these fields will increasingly rely on advanced etching. As these cutting-edge technologies mature, they're going to demand even more enhanced etching processes, and ALE is uniquely positioned to deliver that. So that will fuel even more market expansion, more R&D investment, really pushing the boundaries of what we can build.
And finally, it seems like collaboration, working together, is going to be absolutely key to unlocking this future potential.
Oh, absolutely crucial. Collaboration between the industry players, the equipment makers, the chip manufacturers, and also leading research institutions, technology providers. These partnerships are what will really drive innovation forward. They'll speed up the commercialization of the next generation ALE systems, and the focus will be on developing novel materials, new chemical processes, pushing those etching capabilities even further. It really has to be a collective effort to build this future.
So there you have it, Atomic Layer Etching Systems, ALE. A critical, super precise technology working tirelessly, mostly unseen, behind the scenes. But it's enabling the very future of electronics as we know it. While it might be hidden, it's driving massive change, massive innovation. How we build everything from our personal devices right up to the quantum computers of tomorrow. It really is kind of mind-boggling, isn't it? Controlling materials at that atomic scale, it's almost like, I don't know, building with Lego bricks that are invisible.
It really is remarkable, and maybe this raises an important question for all of us to think about. As our world becomes more and more dependent on these ever smaller, ever more powerful electronics, how will that delicate balance between, rapid technological innovation on one hand, and the significant costs and complexities of precision manufacturing like ALE on the other. How will that balance continue to shape what's actually possible, and maybe even who gets access to these foundational capabilities?
That's a profound thought to end on. A lot to chew on there. Well, thank you for joining us on this deep dive into the world of atomic layer etching. We hope you walk away with maybe a newfound appreciation for those tiny, incredibly complex marvels that truly make our digital lives possible.